Welcome! In this video, we will begin discussing the first excited state for the infinite spherical well. Okay, so that means when L is equal to 1. So this is also the equivalent of Griffiths problem 4.8 as it appears in the third edition of his book Introduction to Quantum Mechanics. So what we have to do here is the following. We want to check that A, that normalization constant, times R times J1 satisfies the radial equation with the potential equal to 0 and L equal to 1. Okay, if you don't know where the spherical Bessel function comes from, then you should probably go back a few videos because we have already derived all of that, and it is pretty important to know where it comes from, even though we are just going to use the result here. Part B then asks us to determine graphically the allowed energies for the infinite spherical well when L is equal to 1. Okay, so basically, first we check that this is the result, then we find the energies. Okay, and we have to show that for large n, the energy value here for n and L equal to 1 is this thing right there. So let's begin with part A. So let's check that this is indeed true for when the potential is 0 and L is equal to 1. So let's begin by writing it down under those conditions. So we have dr squared, and then we have u, but u is going to be a r j1 kr, so we have to take two derivatives of that very soon. Then we have plus, the potential here is 0, so we have plus L plus 1, if L is 1, that is 2, so we get, this would be, let's just put it like this, so this would be 2 h bar over 2m, and then 1 over r squared. And actually, I'm going to write it like this. So 2 over r squared. Now, I'm not going to cancel the 2's. I will not do that. And why? Because what we want to do in the end is just go back to some of the original, to the original u that will soon, actually, I didn't write it down here. I guess I should have done that. You can go ahead and just cancel the 2's. I just like to have them there in case it's useful in some way. So this is AR J1 KR, and then we have, this is equal to the energy times AR J1 evaluated at KR. Okay, so what exactly is R times J1? Well, J1 is this, but we have to evaluate it at KR. So AR J1 evaluated at KR, this is simply going to be A times sine of KR divided by KR squared minus cosine of KR divided by KR. And all of this we have to multiply by R. So here we get K squared times R, and underneath the cosine just K. All right, now we have to take two derivatives of that. All right, so we have to take two derivatives. So let's begin with one. So d dr of u. Okay, so of course the a will not be affected. Then we have sine of kr, that gives us cosine of kr times k divided by k squared r. Then we have plus the derivative. I'm using here the product rule, but keeping in mind that this here is basically multiplying by k to the minus 2 and r to the minus 1. So this is minus sine, simply taking the derivative, kr over k squared r squared. Okay, then we have to take the derivative of minus cosine, which is plus sine. So plus sine of kr times k, the chain rule, divided by k. So now we can do a few simplifications. So this k and this k cancel out, and these two cancel out. Okay, so that is one derivative. So let's now go for another one. So d squared u dr squared, this is a, and now we have cosine goes back to sine. So minus sine of kr times k divided by kr. Then the derivative of this part will give us minus cosine of kr divided by kr squared. And then we have this derivative, which will be minus, that's supposed to be minus cosine of kr times k divided by k squared r squared. And then the derivative of this part will give you another minus sign, so we get plus 2 sine of kr divided by k squared r cubed. And finally we have the derivative of sine, which will give us plus cosine of kr times k. So that is the derivative. So what we now want to do is plug this into this equation and just check that, this does indeed hold. So first, let's multiply by 1 over h squared over 2m. So this cancels out, and here we have to multiply by the inverse of h squared over 2m, so simply 2m over h squared. Okay, that simplifies things a little bit. And let's notice, of course, also that here what we have is that k, this constant k, as we saw when we first introduced the radial equation, is simply the square root of 2me divided by h squared. So what we have here, this and this, is simply, the h squared here is also inside the square root. So when it's outside, it's only h. There we go. So this thing is simply k squared, okay? Okay, with that in mind, let's now just plug everything in. So first we have minus the derivative. Perhaps we can multiply by the minus sign as well. That way, all those many terms do not have a minus sign. So this is minus here, and there's a minus there, so minus. Okay, so all of this, I don't really feel like writing it down again, so I'm just gonna take this and start from there. That way I don't have to rewrite it. Okay, so that is the first term. Then we have, so I just took that. Then we have minus 2 over r squared times a times r. And then we have j1. And j1 evaluated at kr, that is simply sine of kr divided by k squared r squared minus cosine, I'm going to zoom out a little bit, cosine of kr divided by kr. And all this has to be equal to minus k squared. And then we have ar j1 kr. Let's just put u. Okay, so that's simply equal to u. All right, and why do I say it like that? Because eventually we're going to want to go back to u, as we have done in all these problems where we are just checking whether the equation is true. So let's see, what can we simplify? Well, notice we have, let's see, cosine kr times k minus cosine kr times, oh, look at this. This k right here cancels out with the squared. So we end up with 2 cosine kr. So just add those two together. And okay, you can't do much more there. But now let's multiply through by this 1 over r squared. So this here is r cancels out with a squared. So we just have 1 over r remaining. So that means this right there is going to be cubed. And this is going to be squared. So we have minus 2 times sine kr over k squared r cubed, which is precisely the same as this one, but with opposite sign. So this and this cancels out. Then we have plus 2 times cosine kr squared, which is the same as that. So with that, we get minus, or let's actually factor out a first. So we have a factor of minus sine of, here the k's cancel out, so we get kr over r plus cosine of kr times k. And this has to be, is there anything else remaining? No. Okay, and this has to be equal to minus k squared u. So notice here that what we want to go back to is this expression right there, right? This is our u. U is equal to arj1 of kr. And that is a times sine kr over k squared r minus cosine kr over k. So if we take a look at this, first we can see that there's a minus sign. So if we factor out a minus sign, we get sine minus cosine. Then we are lacking k squared down here, so we could multiply and divide by k squared. And also here we have 1 over k, but here we have k. So if we multiply and divide by k squared, or just by k actually, so times k and divided by k. That means we can factor out minus k squared, and then we have, let's keep the a outside. So minus k squared a, and then we have sine of kr over k squared r minus cosine of kr over k, and that is exactly u. So this is minus, so this is equal to minus k squared u, which is exactly what we have on the right hand side. So as you can see, this is indeed a solution. Okay, so we just checked that arj1 is indeed a solution for the radial equation for v equals 0, right? Which is the case of the infinite or finite square well, depending on exactly what the rest of the potential is, and L equal 1. Okay, so now we want to see determine graphically the allowed energies for the infinite spherical well when L is equal to 1. And we want to show that for large n, the energy is that thing right there. All right, so that's what we want to do. Okay, so for part B now, we want to determine graphically the allowed energies for the infinite spherical well when L is equal to 1. And of course, we want to show that for large n, this is going to be a decent approximation. Okay, so how do we find the allowed energies? Well, here you can perhaps go back to the video on the infinite square well where we did this, or just see what we'll do here. Of course, I will show it again. Now, what we will do is keep in mind what our solutions are. So the potential that we have here is 0 if r is smaller or equal than some a, and it is going to be infinite if r is greater or equal than that a. So that is the case where we are. Now, what was the solution for this equation? Well, we know that our solution is u is a r j1 kr. Okay, that's our solution for that case. Now, what is our solution for this case? Well, ur is equal to 0, right? We cannot have a wave function there. It's simply not possible. Why? Because it's an infinite potential. You cannot have a bound state if you have an infinite potential, right? That's not possible. You cannot normalize anything. It blows up. It's bad, very bad. Okay, so that means that for continuity, at r equals a, where those two regions meet, the wave functions need to be the same. That means that a r j1 of kr, rather evaluating, right, at r equals a, we get a and a. So we get small a and small a. This has to be equal to 0, which means that j1 of ka has to be equal to 0. Now, what is that? So j1 is this thing right there. So that would be sine of ka divided by x squared, which will be k squared, a squared, minus cosine of ka divided by ka. This has to be equal to 0. So of course we can just put cosine to the other side and divide, so we get that the tangent of ka is going to be equal to just ka, right? We can multiply and these squares will cancel out, right? So this cancels out with that. Okay, so this is the equation that we get, and this is now the transcendent equation that we need to solve. Okay, and we have done something very similar to this actually in the case for, I believe it was still in the square well. It's actually very similar to this. So let's just say z is equal to ka. That way we get tangent of z is equal to z. Now, of course, you could try to solve this equation in any numerical way or something like that, but we are now interested in doing this graphically. So what we will do is simply sketch this. So let's make a very, very large axis. And there we go. So here we have just our functions of z. And here we have just z. Okay, and this is 0. Now let's just say this is going to be pi over 2 and I don't know, something around here is going to be pi. So this is just a sketch, of course. It's not going to be exact or anything like that. If you want to do this in a more exact form, you could use some sort of sketching software, whichever one you like. You can maybe program something using Python or MATLAB or whatever. This is 2 pi, not 4 pi. That's 4 pi over 2, which is 2 pi. So 2 pi. Then we have 3 pi, and then we have, that would be 7 pi over 2 and 4 pi. And this would be 9 pi over 2, and this is 5 pi, etc. Okay, so what is the graph of the tangent like? So the graph of the tangent right after 0, right? At 0, keeping in mind this is sine over cosine. So that means sine at 0 is 0. And then as we go towards pi over 2, then what we get is going to be that we go to infinity, because cosine of pi over 2, is 0, and you have 1 over 0 or something over 0, which is going to go to infinity. So that means that what we will have here is just something like this. And perhaps I will actually use a different color. So the tangent goes up something like that. And then it comes from minus infinity. So something like this. Whoops. Something like this. It goes to 0 at pi, and then it goes all the way up again. And then it comes from down here again. Whoops. I'm not the best at sketching, but... And then we go like this, and like that. And we go like this. And this is just a very, very rough sketch of what this looks like. Okay. That in blue, we have the tangent of z. And then what we can do is just do the same thing, but for z. And here you can just start going for maybe pi, trying to keep the same distance, of course, if you want to do this kind of proportionally. And somewhere over there, you're going to have 2 pi and so on. So it would have to cross this point and also this point and also a point somewhere over there. So let me just try to draw a line that goes kind of through all of them. Okay, I didn't do it particularly well, but this is a decent approximation. Okay, so what we have here, this is of course f of z equal to z. So this is f of z equal to z. And well, I guess I should also write this as f of z. So what we can see here is that whenever we have the intersections between the blue and the red line, that is our solution. And as we go further and further away, right, as we go to higher and higher values of z, the intersection will occur basically at n plus 1 times pi. Plus 1/2. So what we have here is that the first intersection occurs at 1 plus 1/2, which is 3/2 times pi, right? That's the first intersection. And then the next one will be at 2 plus 1/2, which is 5/2 pi. And the larger and larger our n is, the better this approximation is. Okay, so that is how you can see basically where those intersections occur, right? You can always see just going up. And the more time you take, of course, to actually do this sketch proportionally, this will be more and more evident. So what are the energies then? Well, let's go to the energies of the infinite square. Well, we know that k squared is equal to 2me over h bar squared. And here we just, well, solve for e. So e is going to be, that's h bar squared, k squared over 2m. But what is k? So let's go back a little bit. We know that k here is z over a. So we know that k is z over a. So h bar squared 2m z over a squared. And what is z? Well, z is going to be the values where these curves intersect, which we know are n plus 1/2 times pi. So this would be h bar squared over 2m, and then instead of z, we have n plus 1/2 squared, and I guess we can put the pi squared over there, and a squared there. So there we go. Those are the values for the energy, and as you can see, that is exactly what we wanted to solve. That is, of course, an approximation. It is valid for very large values of n. The higher they are, the more energetic it is. So those are the energies for the first excited state of the infinite square well. I hope that this video made it relatively clear. As you can see, it wasn't particularly difficult. The first part was simply plugging the solution in, deriving a few times, and just doing some algebra. And the second part is stuff that you have done in the past as well. Just do continuity of the wave functions, and that way we can get a transcendent equation, and we just plot that and find some sort of approximate solution. So yeah, I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you in another video. Thank you very much.